Thank you very much. Thank you for introduction. And my name is Isao Ishikawa. I'm working at Kyoto University. And today I would like to talk about the finite-dimensional approximation of a kind of the local dynamics. And I also introduce some application for our theory. So in this talk, actually, I will focus on a data-driven local linear approximation. And then, and I would like to extract some nice information only from data. This is my motivation. So I'm looking forward to sharing decent result for these topics. Okay, this is a roadmap for my today's talk. And first I will explain the data-driven viewpoint of dynamical systems. And then it's a kind of actually it's a kind of learning of dynamical systems. So that's why maybe I'm in this session. And the second, I will introduce some notion of dual jets. But actually, I don't get into the detail of jets. But I briefly introduce this notion, and also I introduce some finite-dimensional approximation or push forwards. And then in the last third, I will show how this leads a reconstruction of dynamical information from finite sample data, flow data. So actually the main message is very simple. And the first dual jet, actually it's very canonical local dimensional model. And then actually it's very very useful to extract some dynamical information of dynamical systems. Okay, let me start with the data-driven viewpoint of dynamical systems. And so let me begin with the basic setting, and I would like to fix the notation I will use throughout my talks. And so a dynamical system is very basic object to my research, and actually the definition is very simple, and we fix a set X, and the dynamical system is just a map F, and I always denote the dynamical system by F, and this is just a map from X to itself. Actually, we always assume that X is a subset of Euclidean space RD, and also we always assume that F is smooth. And in many problems, at least in my research context, we do not know this map F directly. So instead, we only observe sample input-output pairs where each output is the image of the input data under the unknown map F. So our starting point is finite data, not an explicit formula of F. Okay, this is my starting point. Then the question is that what kind of useful information we can recover from such data xn, yy, xn, yn. This is the basic setting. Okay. And the goal is not only to approximate the F, the dynamical system F itself. Approximating the map F itself is sometimes impossible. And it depends on the program setting, but sometimes impossible, or actually not essential. Sometimes it's not essential. Approximating F itself is not essential, or computing the approximating map is sometimes cost too much. So we also want to recover some important structure. Actually, we also want to some nice structure of dynamical system, like the fixed point, equilibrium point, or some invariant set of dynamical system, or attractors. So, and we want to do this without the explicit knowledge of the map F. And so my main question is, how can we extract essential information from finite sample data generated by dynamical system F? This is the goal of the data-driven analysis of dynamical system, and this is the main, my main theme in my study. Okay, Actually, I think there is a kind of very classical problem, and there are many approaches to tackle this problem. And I think that there is one promising methodology to study this problem. The approach is to move from points to functions. So, and then to do this, I introduced the Koopman operators. So the Koopman operator is actually to define the Koopman operator. First, we fix a function space H. This is a function space on X. H, a function space. This is a kind of linear space composed of the function defined on X. Then the Koopman operator is just composing the dynamical system to the function f. It is also called pullback in the mathematics or composition operator. And then maybe the Koopman operator is kind of, maybe this type of linear operator is referred to in, for example, engineering or machine learning. They usually call this linear operator Koopman operator. So actually, this operator is linear even when the original dynamical system is non-linear, and we can define some nice linear algebraic invariant. So the linear dynamics on it means that the linear dynamics on the state X is lifted to the linear non-linear dynamics on X F is lifted to the linear dynamics on function space, and the latter one. This is the illustrative picture of explaining why study of Koopman operator is effective. So when we apply the Koopman operator from the x cubed map to the sine x function, sine function here, then the CF sine x here is actually sine x to the 3. Yeah, the left picture, left figure. Yeah, this is by definition. And actually, you can see that it reflects the property of the dynamical system x to the cube. For example, the sine function is the derivative of sine function at origin is 1, but the sine to the x to the sine x to the 3, the derivative of the at the origin is 0. So it means that it reflects the kind of stability of around the origin, and also so the sine to the x to the 3 highly oscillated if x to the go to the infinity. It means that the x to the cube, x to the 3, the original dynamics go faster to the infinity, go to the infinity faster. So it reflects the high oscillation of the high oscillation of this sine to the x3 reflects the kind of the growth property of x to the 3. So yeah, so even we observe the transformation of only one function under the Koopman operator, we can find many features of the original dynamical system. So thus, if we understand the Koopman operator well, then we can earn more rich information of the original dynamical system. So I think that this simple idea is very powerful, and I focus on this operator to analyze the dynamical system. Okay, so at this point, let me explain why the function space are useful. And then, so from the data side, we want to algorithms that are effective and theoretically guaranteed. And from dynamical system, and we want to meaningful objects such as attractors or invariant set or local stability or something. And the function space, we connect these two sides, using the Koopman operator. Then they will give us the theoretical tool developed in the field of functional analysis. So function spaces form a bridge between data, algorithm, and dynamical system. Today's talk today's talk focuses on the first bridge from sample data to function space. I work on this one. And then second bridge, it has many mathematical problems. Actually, we want to the Koopman operator is a kind of functional analytic object. So we want to, recover the its property of dynamical system from the functional analysis property of Coupon operator. And this includes many Pascal programs. And I also work on this problem, but today I don't get into this problem. And today I will talk about the first bridge, the data-driven algorithm for dynamical system. So in the first bridge from sample data, we try to extract some property of dynamical system using the function space theory. Okay, then let's move to the second part. So where I explain Georgette and the finite dimensional approximation or push forward. So to see my main idea, let me first show a kind of one-dimensional picture. It's very easy, actually it's very elementary. So take a point P in X and let Q be its image under the map F. And now look at the arbitrary function H and its derivative at point P. After composition with F, these derivatives at P are related to the values and derivatives of F at P and H at Q by the chain rule. It is a very easy, and it's a kind of very elementary fact. The important point is that this relation is described by a finite dimensional and triangular matrix. And Coupon operator had rich information, as I explained before. And then, but locally, the Coupon operator is described by this matrix PFM, and built from the derivative of F at P. So this is the first observation that the local dynamics can be written in the finite dimensional linear algebra. Yeah, but in this sense, maybe to understand the Coupon operator, first we work on locally. If we can extract some information on PFM, then maybe at least we can extract some nice information, local information of dynamical system from Coupon operator. Okay, to make this picture systematic, so we look at a kind of the dual jet space at point P. So for each multi-index alpha, alpha is the tuple of the positive, non-negative integers. And then the derivative of function at P is the linear function, right? Then I denote it by delta alpha P. Then if we collect all derivatives at P up to order n, then they span the finite dimensional space on which I denote dPn here. The dPn is the linear span over delta alpha P. So the dPn is a kind of the finite dimensional subspace that record the local Taylor coefficient or a kind of the derivative, higher derivative at the function at P. And actually today I don't get into the detail of this notion, but actually this is naturally identified with the dual of the n jet space. And actually we are not, actually the jet is very classical and canonical object on the manifold, and maybe you can find this nice, this detailed explanation in some classical differential geometry textbooks. But the point is that this is the jet, the dPn is very canonical and then mathematically concrete object. Okay, then now we introduce the push forward on the dual jet space. The push forward is defined like this. This is completed. This is just push forward. This is also a kind of the Coupon operator on the jet space. I mean the dual jet space, induced by the CF. Here lambda is an element of dual jet space, and F star lambda is a linear functional that allocate lambda. It's allocate lambda CF. So by the chain rule, we can easily show that the push forward induces the linear map from dPn to dFPn. This is kind of very important, and its representation matrix actually exactly the transpose of the chain rule matrix PFM, from the previous slide. Yeah. So the dual jet gives a kind of canonical, maybe systematic picture to analyze systematic framework to analyze the local dynamics of a coupon operator. Yeah. Then the problem is that how to compute this PFM from data, and especially the kind of the discrete sample data from dynamical system. Yeah, this is the main object of my talk. Okay, and then actually, it's a kind of artificial. Maybe it looks artificial, and actually, we have a general theoretical framework to construct this type of function. But today I don't explain the details. Yeah. Okay, but let me explain this one. First we assume some maybe we assume that x is RD. Maybe sorry, we don't need this assumption. Sorry, first I assume that x is a kind of subset of the RD. So sorry, it disappeared. Okay, and then we fix the base point p. Then we define that for each sample point x data, for each data, define a local, we call this function a local jet feature function. And we define the vn1 nd by this function. And epx and the kind of the exponential function times polynomial and the square root of the fraction of n1 nd is a kind of the normalization, and then we define the jet feature vector like just the vector by the function defined by these vn1 nd. And yeah, this function is a kind of artificial, and maybe but yeah, if we introduce the notion of RKHS reproducing kernel Hilbert space, and then this is the image of the dual jet space into the RKHS via the kernel mean embeddings. Maybe if you know the theory of RKHS and some related topics, maybe you can understand what I said. Yeah, but actually this is very. The point is that this is theoretically. Deduce this function is theoretically deduced functions. Yeah, but in this case we describe everything explicitly. So yeah, so we define this function. Then let me now state the data-driven approximation of the local PF, local and the matrix defined on the dual jet space. So yeah, we fix a base point P and sample input out data pair X and Y, and target, and then we fix a target order. We fix a non-negative integer M, and we call it the target jet order, and we also take some L, non-negative integer L, and we call excessive jet order. From this data, we want to construct a matrix white hat C, and then the matrix X is our estimate of the push forward on dual jet space, and we explain later. Next slide. Okay, the algorithm is very simple, and first we built the local jet feature vector from data X and Y. The order is n plus L, and then we find. Then next we solve the least square problem of the larger feature space. Yeah, and we denote the solution by B star. Yeah. Then third we take actually this matrix B star is a kind of the best linear fit of the observed data in the larger feature space. I will explain later. And then third, we take the principal block of the matrix. Yeah. The smaller blocks is our estimate, of the local push forward on dual jet space. And actually we can mathematically prove that this the upper left part actually converges to the push forward on the dual jet space PFM. Let me explain some relation between the other method, very standard method, EDMD. And EDMD is it's abbreviation of extended dynamic mode decomposition, and it is proposed by Williams in 2005. And this is now it's a kind of very standard method in data-driven analysis or group analysis in my research. And EDMD is, in EDMD, we first choose a dictionary function, phi I, and then we solve the least square problem to find a matrix that best fits the data in that feature space here. Until this time, this is almost the same as the previous algorithm. Then the algorithm level, the setup is almost the same as ours, but the important difference is that meaning of the feature space and in the meaning of the output matrix. Okay, so in our approach, the key point is using a local jet feature as a basis in our dictionary, and we do not use the arbitrary dictionary. And this is this picture is a heat map of the matrix of Vista. Then in our method, in our approach, rather than keeping the entire matrix, we focus on the small, meaningful principal blocks. And actually, the principal block actually converges to the dual jet, the push forward on dual jet. But so the distruncated matrix push forward the dual jet on, and then the upper left part gives us a concrete, interpretable object, mathematical object. So in other words, our truncation makes the model locally accurate and much easier to connect with underlying some canonical mathematical machinery, mathematical structure. In contrast, EDMD uses the for matrix which may fit the data globally, but makes interpretation much harder. And then this is one of the challenging problems in the theory of DMD. And so while EDMD and our methods share similar computational structure, but our focus on jet. Our focus is we focus on jet and provide a clear local meaning. Yeah. Okay, so now I moved on some application of this method. And first, I show some rough picture to estimate the generator for the push forward in the data-driven manner. So suppose that now that our data comes from the flow map of the vector field, F, yeah? So we consider this ODE. And then from these sample flow data, flow map data, then we first compute the estimated local push forward matrix. Then we take its logarithm, matrix logarithm and divide by the time step, t, delta t. Then this gives a kind of generator. Yeah, and this from discrete time sample data, then we recover local infinite information about the underlying vector field. So in this setting, we have a data from x and phi delta tx, the pair of this data. Okay, first we explain the equilibrium point detection. This is the kind of zero-dimensional infinite. This is the kind of the detection of zero-dimensional invariant set of dynamical system. So the observation is very simple, and actually the matrix, the target matrix, has a kind of structure of the block triangular matrix structure. So, and we can show that if P is the equilibrium point, it means that P is a kind of the fixed point of the dynamical system, the dynamical system, then we can show that the output matrix has in the form of this one here, and the lower block EP here, the lower block should be close to 0, and also the So this implication actually motivates the equilibrium score delta P. So we can we can see that that if the score delta P is small, then the point P likely close to the equilibrium point, and so the method gives a direct local test for equilibrium points from sample flow data. Yeah. And actually, it depends, but actually we can prove that this implication is actually necessary and sufficient. So if theoretically, if we have the sufficient many data, then we can show that if the EP is equal to 0, then P is the fixed point, the equilibrium point. So this is here is an example of Duffing oscillator. Yeah, we consider that this x dot is equal to y and y dot is 0.5 x minus y by 3. And then on the left, the image, we use the data here. We use the data, and x is the input, and y is the kind of green. Plus is the output, and we know that each pair is we know each pair. We use each pair to compute that the equilibrium score delta P using this data. Actually, this system has the 3 fixed points here, and then if we start this, for example, this initial point here, then it's actually converged to one of the equilibrium point. No, 2 of equilibrium point, and this is unstable fixed point. Then, when on the right, you can see that the heat map of the equilibrium score delta. Then, the minima of the score matches the equilibrium point structure of the system very well, and even the data is outside. Maybe the data does not cover the equilibrium point, we can detect the equilibrium point. So this example shows that the score is not only a formal idea, and actually it works, and we can detect some invariant structure of dynamical system. And actually, we can use this matrix or the reconstruction of the vector field. So first, we have in this setting, we assume that the base point P is equilibrium point, and DFP are real. Maybe we don't need the eigenvalue assumption, but but for safety, so far we assume the delta P is real, and then the input data is the data generated by dynamical system here, described like here, and then from these data we compute the estimated push-well matrix, and then compute the local generator, and you taking a log matrix log, and then finally for generator we define the reconstructed local vector field. Actually, the formula in the last formula is a little complicated, but you don't have to check all the detail. But the point is that the f hat, the last formula, can be computed from the data and get featured vector v, and everything can be computed from data and some x-bit function. And actually, we can show that this f hat actually converges to the original dynamical system f. If f has the f has some nice analytic property, more accurately, f has sufficiently large domain. F can be analytically continued sufficiently large domain. We can show that the f hat actually converges to the f itself. Okay, and then let me show the numerical simulation for the Lorentz system. Here is the Lorentz system is kind of the benchmark in my research group, research community, and then everyone uses the Lorentz system to confirm the performance of the method. And we use nearly 70,000 distinct initial points sampled from this region, minus 10 to 10 square cube, that kind of cube domain. And then for each initial state, we generate a pair after a short but relatively long time evolution, 0.21 here, yi. Then we see that how well our estimated model captures nonlinear dynamics from purely sampled data. On the left, this is a visualization of the sample input-output pair in the state space. Where you can see that each point are relatively far from here. And then on the right, you can see the comparison between the real data and the exact data and true data, our prediction of the sample trajectory. And also, I put some very classical method and finite difference method and using the kind of regression. Now, actually, it doesn't work because each point is very far, and we can compute the derivative at each point. So such a finite difference method, it does not work. But using a kind of this operator theoretic investigation, operator theoretic idea, then actually it's reconstruct the original dynamical system. Okay. So this is let me finish with the main message. Then the dual-jet gives canonical local finite dimensional model for nonlinear dynamical systems. It is a very mathematical, canonical, and then very nice. And this model can be estimated from sample data with convergence guarantee in the analytic setting. And the same framework also gives the practical and applications such as equilibrium point detection and reconstruction of analytic vector fields. So, okay, so thank you very much for your attention, and I stop here.
Yeah, so in this method, so instead of directly looking at the nonlinear function, but you look at various map of functions.
Mm-hmm.
In that way. And so you wrote the age. And in this case, the choice of age is relevant or?
No, actually, we try to find a kind of the not one age, and it's a kind of the a set of, yeah, or kind of global, maybe this, yeah.
Then, in order to linearize, because you need infinite many, so you have to trunk. And so the trunk, if you don't do the truncation, of course, any h is fine. But when you truncate,
Okay.
So you need to select some specific.
Yeah, and actually, in this case, we take a dual, but in the context, we use the jet or dual jet function, and I don't explain well, but the dual jet actually can be realized in RKHS, and the dual jet space is we can regard the dual jet space as a kind of finite dimensional space of functions. So maybe in this context, the dual jet space is the truncation. Truncation.
Yeah. So linearized one has needs the information of derivative of it.
Yes.
So. Yeah. Okay. So could you show the example? Yeah. So that's
this one. Okay.
So there are three. Graph one is the
Yes.
The green one is the linear length.
Blue, kind of blue one. Sorry, it's a bit hard to see, but the black thick one is the true one, and the blue thin one is the blue thin one. It's a kind and this a bit this here. Sorry, so yeah, this and I mean that this black one is the true one, and then a bit thin. Yeah.
And green one.
Green one is the our method. I use it the
Oh, this is the
Koopman. Yeah, using the Koopman operator method.
And the
Red one is the finite difference method. Actually, I use the. I mean the if y and x is very close, then we can explain. We can approximate the delta t over yi minus xi, right? If yi and xi is very sufficiently close, then we can we can approximate the f derivative at xi. So in this case, we we compute this computation, and then using this data, and then use a kind of the regression, and then approximate f directly.
that's the most naive one.
Yeah, very naive one. Yes.
And so it seems well, okay, so naive one, so the improvement by this method is only near the t equal, around t equal 0. So for other regions, where, the red one diverges.
Yeah, diverges. Maybe yeah.
Okay. Oh, so this here shows that this jet method can reproduce very well.
Yes. Yes.
And so how many what's the size of the
Truncation and with truncation is actually two, and truncate size of truncation is and sorry, this is also sorry, it should be L, and this so this is 3.3. So we take the target jet order is 2, and then the excessive order as we take excessive order as 33. It's I'm not sure, but we can. There's several factors, and one is that the Lorentz equation is defined by the polynomial. So actually our method is guaranteed only for such a this method, and actually we can show that it actually converges to the true function. Yeah, and so this result is actually theoretically guaranteed, so actually converge. Yeah, but but actually Lorentz equation is actually defined by polynomial, so that's why it works. So.
So what's the relation of your approach to Haken's theorem, where you can reconstruct the dynamical system itself? Is it like a derived version?
Yeah. Okay. I think there is no direct relation between because the Haken's theorem is a kind of the reconstruction of the topological information of dynamical system, right? It's a kind of but yeah, actually, but it works because that the Haken theorem is take the kind of data of I mean how to say the delay embedding. So the delay the width of delay is goes to 0. It's a kind of the jet or derivative of its data. So yeah, actually it's a kind of But actually, I'm not sure. But there is a relation, but there is some relation. But I'm not, yeah, but I'm not sure about that. Yeah, so yeah, mm, mm, yeah. But I think there is a relation. Yeah.
I think we can talk in a minute. Thanks, Steven.
Thank you very much.